Same angle, same shape. Ratios stay constant. Name sine cosine tangent.
High on the granite ridge, Slate, the mountain goat, climbs a steep, unyielding slope. She moves upward at one steady, unchanging incline. Watching from below, I can see that as Slate climbs, she traces distinct paths into the rock. Low on the ridge, she forms a small right triangle. Higher up, she traces a massive one. Look closely at where Slate begins both climbs. The corner angle at her hooves is exactly the same in the small triangle as it is in the large one. Because they share that identical corner angle, these two right triangles are mathematically similar. They are the exact same shape, just scaled to different sizes. If these shapes are just scaled copies of one another, it raises a question. Do the proportional relationships between their sides change when the triangle gets bigger? Let's test the numbers painted on the rocks. On the small triangle, Slate's vertical climb, the rise, is 3 stone ledges. The horizontal distance, the run, is 4 paces. Higher up, the rise is 6 ledges, the run is 8. Dividing the rise by the run for the small climb gives 0.75. Dividing 6 by 8 for the large triangle is identical, 0.75. Because the triangles are similar, this ratio holds true at any scale. We call this specific constant the side opposite the angle divided by the adjacent side, the tangent. Let's shift our focus to the slanted goat path connecting the start and end of Slate's climb. In geometry, this longest side is the hypotenuse. Measuring the slanted paths, the small path is 5 units long, the large is 10. The vertical rise numbers remain 3 and 6. Comparing vertical rise to the slanted path, we get 3/5 for the small climb and 6/10 for the large. Both calculations yield the exact same result, 0.6. The angle dictates this climbing relationship, regardless of the distance traveled. We call this second locked ratio, the opposite side divided by the hypotenuse, the sine. That leaves one final pair of sides. We look at the flat rock shelf at the foot of the slope, the run, and compare it to the slanted path. On the small triangle, we divide a run of 4 by a path of 5. On the large, a run of 8 by a path of 10. Both equations evaluate to 0.8. The final proportion holds true. This constant ratio, the adjacent side divided by the hypotenuse, is defined as the cosine. This reveals the golden rule of similarity in right triangles. Because similarity scales all sides evenly, locking the angle permanently locks every single side ratio. Fixing one acute angle creates one locked shape, yielding 3 unchangeable ratios at every possible size. These fixed values are properties of the angle itself. Because they remain constant at every scale, they allow us to calculate the measurements of any right triangle as long as we know the degree of the slope. Slate bounds effortlessly up to the peak of the ridge, her path dictated by the unbreakable rules of the rock. Before I leave you, consider this new slope. It rises 5 ledges for a run of 12 paces, giving a slanted path of 13. Use what we've discovered here. Calculate the sine of this new climbing angle. I'll see you at the next bend.
Opposite over hypotenuse. Adjacent over hypotenuse. Tangent compares legs.